Hey there everyone, I hope you guys are doing well. You know, if there's a current in a wire within the vicinity of a magnetic field, then this current will feel a force, and this force is equal to the current value times the length of the wire that is exposed to the magnetic field, times the magnetic field value, times sine theta, where theta is the angle between the direction of the current and the magnetic field direction. Okay? So some engineers paid attention to that force and they said, hey, if there is some kind of wire within the vicinity of magnetic field and this wire is carrying a current and it can feel the force of magnetic field, then what if we built a loop within the vicinity of a magnetic field like this one here, and this magnetic field, let's say it's going from left to right, and this loop carries a current that is valued at I, and this current goes through the closed loop like that within some kind of like circuit design. Okay, so I all the time, right? And this length here of the loop is L. The width of the loop, I'm gonna call it W. All right. If we have this kind of like design, can we make this loop rotate? And the answer is yes. Let's see how that works. Let's see. This is the magnetic field going from left to right. We know the magnetic field by the right-hand rule is represented by our four fingers. So it's going from left to right, and this is my right, so it's going this way. Okay? Remember, my left is your right and your right is your left. But the magnetic field for me, or on the page or on the screen, is going to the right, this direction. And as you can see, the current is my thumb. The current is my thumb, like this. Magnetic field, current. So the force of the magnetic field will be the palm of my hand, and that's going into the page. So if I go here, that would be going into the page, and that's the force on the left side of the loop going into the page. Now let's go to the right side of the loop here, on this one here. Alright, so the magnetic field is still going to the right, and the current is going down. So the force, the palm of my hand, will be out of the page. So on this side of the loop, the force is out of the page. Okay? Alright, now let's see what on this loop here, this part here, and this part here. Okay, so this part here, the upper part, has the current going this direction and the magnetic field in the same direction. So as you can see, they're parallel. The angle between them is 0. So sine 0 is 0 and the force will be 0. So the force coming from here will be 0. And here, what do you think the force is going to be? The current is going this way, this direction, and the magnetic field is going this direction. The angle between the two is 180 degrees. Sine 180 is also 0, so the force here will be also 0. So basically, what is this telling us? That the upper part of the loop and the lower part do not contribute to the force, and thus they do not rotate or help in the torque that needs to rotate the motor. Okay? So now we agreed. So I'm going to call this part 1. I'm going to call this part 2 because they are the only two parts that are contributing. Now, if I was an engineer, I'll bring something here in the middle exactly, and I will put what we call an axis of rotation. Why? Because if this force is going in and this force here is going out, and we put an axis of rotation, what happens is the loop is going to twist. It's going to twist like that. Okay? And because of inertia, it's going to keep twisting and twisting and twisting. And let's look at that in detail. Remember, the torque is equal to Rf sine phi. Okay? R is what? The distance between the force action and the axis of rotation. So this is the force action here. This is the force action. And this is the axis of rotation. So my R for this equation is here, which is exactly middle way between this part and this part. Or I can say that R is equal to W over 2 because this whole thing is W. F is the force coming from the magnetic field, so I'm going to say that's FB. If it's on the left, I'm going to call it FB1. If it's on the right, I'm going to call it FB2. Okay. Phi is the angle between the action of the force and R. Let's look at this situation here to understand this very well. Look, the magnetic field force is going in. So that's going in, right? And the current is going up. Now look at this here. The angle is what? 90 degrees. In and up, right? That's in and up. So the angle here is 90 degrees. So at the beginning, it's 90 degrees and it's maximum torque because sine 90 is 1 and sine 90 is 1 at is the maximum value for sine 90. All right. So, but we're going to leave this here as like a floating variable. It changes all the time. All right. We're going to look at it later. I just wanted to let you know at the beginning when it's like this, angle phi is 90 degrees, which is maximum. Okay, now let's look at this in detail. Now torque, I'm going to call it tau, is equal R, which is W over 2. I'm going to look now at this situation here on the left, or 1, times FB1, which is I, L, B. Now what is theta? Look, theta is the angle between the magnetic field and the direction of the current. Look, the direction of the current is up. And the magnetic field is this way. Look, the angle is what? 90 degrees. Okay? So here, that's 1, because sine 90 is 1. So I'm not going to put it here in this equation. And that will be times sine phi. Okay? Now, I'm going to call this torque number 1 because it's on the left. Now, torque number 2 is equal to the same thing, W over 2 times the force FB, which is the same current, the same length, the same magnetic field, times also the same angle, but in the opposite direction. But sine is not going to make any difference, whether it's above 90 or less than 90. So now, if we want to find the total torque, we just have to add this together. Total torque is equal to torque number 1 plus torque number 2, and they are equal exactly, as you can see. So just basically take 1, multiply it by 2, and that would be equal to W instead of W over 2, I, L, B times sine phi. Okay? Now let's look at this little thing here. W and L, where is that? So that's W, right? And that's L. If you multiply these with each other, what you get is the surface area of the loop. So I'm going to exchange this with surface area. Then I'm going to write this again, that the total torque is equal to I, A, B, sine phi. All right? Good. If you are an engineer, you're not going to just make one loop here. If you are an engineer and you want efficiency, you will make hundreds of loops if you can. Let's say a total number of loops that is equal to n. So we're going to say for n loops, you will have a bigger torque that is equal to number of loops times I times A, B sine phi. Okay? Well, that's nice because now you multiply the torque by hundreds of numbers if you want to. So that's why those electric motors are super strong, super strong. You can use them to drive a car if you want to. The fan, I mean, like, can you see how far and what the torque and the power on the fan is, for example? So these are very powerful machines, all right? Now I can rearrange this equation because I like to write it this way. So N, to make it easier to remember, N, B, A, I for the current, times sine phi, and that's the equation. You know what NBA is, right? So that's easy to remember. So the torque in an electric motor is NBA I, the current, times sine phi, where phi is the angle between what now? Well, the angle between the area and the magnetic field. So let's look here. So the magnetic field is going this way. This is the maximum situation we said at the beginning, right? Remember, area is a vector quantity, and the direction of the area is perpendicular to the area itself. So look at my hand, the palm of my hand. What is the direction of my hand? It's actually out, perpendicular to my hand, okay? If you have any kind of like surface like this is a surface, as you can see. What is the direction of that surface? Is perpendicular to the surface. So that's good, because if the magnetic field is going this way, the direction of this is perpendicular to it, which is out of the page, so 90 degrees, right? So the angle between the surface area direction and the magnetic field is 90 degrees for this, and that's how you get max. So you can say, if you want, tau max or torque max is equal to NBA times the current. Again, n number of loops, B is the magnetic field, A is the surface area, I is the current going through the loop. So a quantity of historical importance is known as the magnetic dipole. So the magnetic dipole known as mu, and mu is equal to N A I. So that's a very important quantity. So if you want to rewrite this whole equation, torque is equal to mu times magnetic field times sine phi. So that's another form you can write this equation, because mu is equal to NIA, B sine phi, and that's it. Okay? That's it for the electric motor. We will have examples next time. Thank you for watching. Bye-bye.